when evaluating the financial consequences of alternative projects or designs in civil engineering infrastructure, it becomes necessary to have tools, mathematical tools, to compare what would otherwise look like apples and oranges. That is, to compare different cash flow expectations on a basis that is consistent for both projects. Let me see if I can think of an example that presents the obstacle. You might be trying to decide whether to do a small project or a large project. Suppose there's a new factory under consideration, and they could build a small factory anticipating less demand and then expand it later. That's one cash flow diagram. Perhaps they invest $100 million now, and they say, if the market grows, we'll invest another $200 million in 10 years to expand it. But they know that if they build the entire factory all at once, that is, if they anticipate the growth now, it will be cheaper instead of adding on later. And so perhaps they say we could build the larger factory, but it would cost us $210 million to do it all at once. And the maintenance costs will be a little bit more every year, and the market won't really grow for another 10 years. These are two different cash flow diagrams. The first one has less upfront expense and then more expense later on. And the second one has more upfront expense and no additional capital investments later on. How should these alternatives be compared on a mathematical basis so you can choose the design alternative that has the greatest expectation of financial reward? That's what this video is about. The simplest way to do it is called simple payback period. So here's an example. I'm considering buying a machine, a CNC router. This would be a computer-driven cutting machine that could cut foam or wood, sometimes other materials, according to a pattern programmed in a computer. So a draftsperson does a drawing, you put that in the computer, and you load your plywood or your foam or whatever it is into your CNC router, and it will cut it out perfect every time. Suppose the CNC router costs $20,000. Why would I buy it? Because I'm thinking I might save on labor. It's very labor intensive to make these cuts. And if I have them automated with this expensive machine that's driven by a computer, perhaps I can save myself 6 or 7 labor hours per unit. That's one cash flow diagram. A big investment of the $20,000 in equipment purchase, maybe a little more for training, and then the savings, the labor savings per unit. And you already have the tools from our equivalence chapter, equivalence of money, to reduce this cash flow diagram to a net present value. But simple payback period is a different way of evaluating a project. The alternative would be to continue to hand cut these units as we have in the past. So you now have a choice between two alternatives. And simple payback period asks the question, in what unit of time, that is, how much time will it take to recoup the investment of $20,000 in equipment? Draw yourself a little cash flow diagram if that helps. I'm going to spend $20,000 now. I'm going to save 6 hours per unit. And suppose the rate at which I charge out labor is $100 an hour. This makes the math a little easy. So $20,000 now, $600 per unit saved in labor costs. If I'm making 10 units a week at $600 of labor saved, I'm saving $6,000 a week. The machine would pay for itself in less than 4 weeks. The labor savings would allow me to accumulate or to repay a loan, for example, in excess of $20,000. And a 6-week payback period is excellent. Simple payback period does not account for the time value of money. There is no interest rate or discount rate considered in a simple payback period. And that is the fundamental, most important advantage because the calculations are so easy. When the time frame is very short and the discount rate or interest rate is small, single digits, the simple payback period will reliably guide an engineer in comparing alternatives, that is, trying to decide where to deploy capital. So what do I mean by short? A lot of companies will insist when they're using a simple payback period analysis, they will insist on a payback period of less than 1 year, which is outstanding. If your cost of capital is low or you're a little bit more forward thinking, you might say, well, we'll do projects with simple payback periods less than 3 years, which is still very good. Because the projects, perhaps they're replacing a piece of equipment that requires a lot of maintenance, and they want to, they're willing to incur the capital cost of replacing the equipment in order to save on the maintenance. When the simple payback period is less than a year, you don't need an interest rate. You don't need a discount rate because that project is so, the expectations for that project are so high, so lucrative that doing the finer algebra to nail down an exact calculation that accounts for inflation or discount rates is pointless. You just pick any project that has a payback of less than 1 year, you do them until you run out of capital. And then you make a new list of payback of less than 1 year, and you do those projects when you get more capital. So as a rule of thumb, when interest rates or discount rates are low, 10% or less, and the payback periods that you expect are short, 3, maybe 2 years or less, simple payback period is an advantageous rule of thumb for comparing different project alternatives. It scales to a project of any size. You can calculate a simple payback period for a $20,000 project or a $20 million project. But not all decisions, for example, the $20 million project, they don't conform to these assumptions of low discount rates and short payback periods. And so it's helpful to have more sophisticated ways to evaluate projects so that you can compare among choices when you know these choices are mutually exclusive. That is, one choice excludes the other. We have a formula. We have a set of formula. But the one that comes in handy often is P equals A times the quantity 1 plus I raised to the n, number of compounded periods, minus 1, all over I, the discount rate, times the quantity 1 plus I raised to the n. Any single variable in that formula could be used as a basis for comparison. For example, you might have 2 different projects with different durations, that is, different time horizons, and they might have different upfront investment or capital costs. They are both reducible to a present value. They are both reducible to an equivalent uniform annual series, an A. That is, what is the equivalent payment over time, a constant payment every month, for example, or every year, that the cash flow diagram could be reduced to. This formula and this approach comes directly out of chapter 14 in our book, Revelle, Whitlach, and Wright, Civil and Environmental Systems Engineering. You use the equivalencies so that you can compare these different projects either on the basis of net present value, P, or on the basis of equivalent uniform annual series, A, or on the basis of I, the internal rate of return. They have advantages and disadvantages. The advantage of using P, the net present value, is once you've net present valued out the 2 projects as they're represented in their cash flow diagram, you have a very simple comparison to make. You just simply choose the alternative with the greatest net present value. And it takes into account the time value of money. That is, It accounts for your discount rate or your interest rate, and therefore it is applicable to long time horizons or those projects where the discount, you might be operating in a high inflation environment or the discount rate or interest rate is very high. Another advantage is it's easy to understand. But the disadvantage of net present value approaches is it doesn't really take into account projects that are vastly different sizes. That is, a $100 million project requires a lot more capital than a $10 million project. And it's likely to have a larger net present value. If the capital is available to you, fine, you might choose to invest so much. But if capital is scarce and you have two projects with different capital requirements, you might apply a different discount rate to the larger project because it's so much more difficult to raise more capital or because it's so much more risk in your computational analysis. Or you might wind up being misled by the present value of the larger project being so much greater. In that case, internal rate of return could be a better way to compute or to compare two project alternatives with different capital requirements. The $10 million project will have one internal rate of return, and that is I, the interest or discount rate that sets P equal to the present value, the discounted value of all the future cash flow expectations. Internal rate of return, which comes out the exact same formula, has the advantage of being scalable. Now you can compare two projects of different sizes, whereas it's more difficult to do, or net present value could lead you astray. Another way to think about it is to convert everything to a future value rather than a present value and say, I want to choose the one that will leave me with the most money at the end of the project duration. To do that, you must pick a future point in time. Present value, the time's picked for you, t equals 0. But future value, you have to say, I'm going to imagine where I am in 10 years or in 20 years or in 50 years. I want to choose the design alternative that will create the most amount of money for me at that common point in time. And it's still subject to the same potential misconception as present value, because larger projects will appear to be more valuable even if they have lower internal rates of return. Finally, this is the most complicated one, the incremental rate of return analysis. When you have two different cash flow diagrams, particularly when they have two different types of capital investment, two different sizes. And you know that either the present value approach or the future value approach might lead you astray by favoring the larger project. You can use an internal rate of return. However, there are times when you would accept a lower internal rate of return for a greater present or future value. And this is when the incremental rate of return analysis comes in handy. Should you go with a larger project, even if it has a lower incremental rate of return? So when you compute the incremental rate of return at the margin, so this might be the delta incremental rate of return, the difference in incremental rates of return between a smaller project and a larger project. There's a particular way to do it. Subtract one cash flow diagram from the other. Create a new cash flow diagram. This would be a third cash flow diagram that represents the difference between the two. When you get the difference between the two cash flow diagrams, this is the incremental cash flow diagram. What is the change in the cash flow diagram that results from going with the bigger project? That's your incremental or your delta cash flow diagram. Then use your formula from chapter 14, your equivalence formulas, to compute the internal rate of return of your incremental or your delta cash flow diagram. When that internal rate of return is negative, it says, don't go with the bigger project. Your capital, your rate of return is going to get so much worse. When the incremental, the delta internal rate of return is positive, it might say you could get a better rate of return by increasing the size of your investment, going with the larger project. And that all makes sense. However, the minimum acceptable rate of return within your company or your organization might be your guidepost. In any evaluation in which you're using incremental rate of return analysis, typically you would compare it to a threshold or a standard within the organization that represents their minimum acceptable rate of return. Just like you might have a rule of thumb that says, well, in our company, we don't invest in anything that doesn't have a better payback period of 1 year or less than 1 year. You might say, we won't invest in any project that doesn't have an incremental rate of return that is better than our minimum acceptable rate of return of 20%, 30%, whatever it is. However, when you're using this incremental, this delta IRR, the minimum acceptable rate of return may not apply. Don't compare your delta internal rate of return to your minimum acceptable rate of return. Instead, you have to have an idea of whether the larger project with a larger delta incremental rate of return is worthwhile in its own right. Your rate of return could get larger if you make the project larger, and that will result in a positive delta or incremental internal rate of return on the difference between the cash flow diagrams. Whether the increased incremental or delta internal rate of return between the two justifies the additional expense, that's still a judgment call. Your assignment now is to make sense of this little lecture by writing out for yourself a table that shows the advantages and disadvantages of each method as you've understood them from my explanation in your reading of chapter 15. In that table, have 3 column headers: method, advantages, disadvantages, and use rows for net present value, future value, equivalent uniform annualized cost, internal rate of return, simple payback period, and the delta approach, that is the incremental rate of return that is calculated from the subtracting one cash flow diagram for another, and then applying the chapter 14 time equivalence formulas to compute an incremental internal rate of return. In another video, I'm going to talk about benefit cost, which is another approach within engineering economics to evaluate the feasibility of an infrastructure improvement project.